Welcome back. In this video we will do a little bit of revision. We will solve this exercise where we will start by modeling, then we will determine the equilibrium points of the system, we will linearize it if necessary, then we will determine its transfer function, and finally we will do simulation. So we will cover again and we will discuss again about everything starting from the beginning of the module. Alright, so we have a cylinder. We see here this is a cylinder from the side. It has a mass m. It has a certain radius r. And let's say we apply an external force F. This is our force applied to the system. So this will be the input. The spring has a certain natural length, L uppercase. And let the position of the object on the inclined plane be denoted by x. This is the x-axis, this is the y-axis, these are the positive directions, and as you see here from the convention we're using, clockwise rotations are considered to be positive. Another force apparently is the restoring force Fs of the spring, and I'm going to tell you that Fs is given by this nonlinear equation. So we have a nonlinear spring, which is not governed by Hooke's law. It's not an elastic spring. Instead, the magnitude of the force, the magnitude, is given by K1. Let's put a minus just to remind us that it has the opposite direction compared to the displacement. K1 times x minus L, K2 x minus L to the power 3, where K1 and K2 are just some positive constants. Without this second term, if it were like that, we would have a simple linear spring. So that's one thing. Now the first task, before we can even do modeling in the sense of writing down equations, we should sketch and draw all the forces that are applied on the cylinder. One force that is very easy to figure out is the weight, m times g. Of course, it's not very convenient the way it is because the main axes, the principal axes we're using here are x and y. So why don't we go on and decompose the weight into a horizontal component, mgx, and a vertical component, mgy. Now look what's going on here. This is angle phi. Here, if you focus on this triangle, this is a right angle triangle. This is a right angle down here. So this is phi. This is 90 degrees. So this one is what? 90 minus phi. And the same goes for this angle. This angle is 90 minus phi. Therefore, this angle down here is angle phi as well. This is phi inside here. So mgy, which touches phi, is mg times cosine phi. And mgx, which is opposite to phi, it is here, is mg times sine phi. So what do we have along the x-axis? We have mgx, which is mg sine phi. We have F. We have the restoring force of the spring. Why don't we write them down? What are the forces along the x-axis? The x-axis. We have the restoring force of the spring. We have our force. We have mgx. Anything else? Well, let's think. This is supposed to move up and down on the inclined plane, and at the same time rotate. We have to write it down actually. We have a no slip condition, meaning these surfaces here can develop adequate friction so that this object will not just slip on the inclined plane. It will not slide, it will roll. For it to roll, it means that it rotates. For an object to rotate, there must be a force that makes it rotate. It's impossible for something to rotate without a force being applied to it somehow. And that force is, let me use some different color, green for example, that force is a force T, which is the friction. This is exactly what makes it rotate. So think of this force T as the cause of it rotating clockwise. So we also have the force T, which is again along the x-axis. And what is the total force along the x-axis? I will write it up here. Respecting the convention, so F is positive, mg sine of phi is positive, T is negative, and the restoring force is opposite to the displacement. Okay, so this is the total force. And what do we know by Newton's second law of motion? We know that the total force is equal to mass times acceleration. So that's everything about the x-axis. Let's have a look very quickly at the y-axis. Y-axis. Now what forces do we have? mgy. Of course there must be another one, because was it just for this force to be applied here, then that would imply by Newton's second law of motion that this object would accelerate towards that direction. But this isn't happening, and the reason it isn't happening is that there is a reaction from the floor applied towards the object. Let's denote that by n, and let's write down the following not very useful equation. It's correct, but it's not really useful because it doesn't really contribute to the dynamics. What we need to find out here is what governs the horizontal motion of this object, and of course the rotation. Now, equation number 1, this equation up here, involves the displacement x, which is brilliant. This is mainly the variable of interest here. It involves F, uppercase, which is the input force. So it involves the input, the state, or the output. If we can measure it, we can call it an output. And also it involves that friction T, which is unknown. The way to find T is to think about the rotational motion that we haven't taken into account so far. So let's focus here on the cylinder and let's figure out what are the torques with respect to this point O, the center. We have that force T that generates with respect to point O the torque T times, let's see here, what is that distance? It is the radius. So we have the force T, and here we have the radius R. So what is the torque? It is force times distance from the point O, which is T times R, and it is a positive torque because it tends to rotate the object in the clockwise direction, so T times R. Brilliant. And we know from the rotational counterpart of Newton's second law of motion that the total torque, and this is the total torque, no other force, none of the other forces generates a torque. The reason is that all of these other forces run through this point O, so the only force that has the tendency to rotate the object is T. So we know from the rotational counterpart of Newton's second law of motion that this is moment of inertia times angular acceleration. So this is written like that, which is T times R. From this equation we are hoping to find T somehow and plug it back in here to eliminate T and have something more handy, more useful. Now what is the moment of inertia of a cylinder? It is 1/2 mr squared theta double dot, let's write the rest, equals TR. Let's get rid of R from both sides of the equation, have R on both sides. Let me write it down again. And this is an equation for T. Nevertheless, here we have X and here we have theta. We need to do something about that. There is a relationship between theta, so the angular, think of it as an angular displacement, and the linear displacement. So how much we move along the x-axis is a function of how much the ball rotates. And how much do we move really? We move as much as the arc covered by that angle. Let me sketch it here for you, maybe not on the inclined plane, on a level plane. So you have the cylinder here, and after a while the cylinder is here. So that is here, and then it goes there, for example. What is the distance between this point and this point? What is that distance, x? It is the same as this length. This length here, the length of the arc. Okay, maybe the sketch is not ideal. This looks longer than this one, but you get the idea. So this is theta, this is r, and this is the arc length, which is exactly equal to x. Now think of this thing as a slice of pizza. What is the length of the crust x? It is r times theta. Now differentiate both sides and you have x dot. R is a constant, so r theta dot. Differentiate once again and you have x double dot is r theta double dot. And what do you see? You see here r theta double dot. This is exactly x double dot. So from here we obtain 1/2 mx double dot is equal to t. And from equation number 1, there is just enough space down here to write our final equation. We have f, I'm copying from up here, so f plus mg sine phi minus 1/2 mx double dot. Where did that come from? Came from here. So t is equal to that. Last but not least, you see mx double dot on the left hand side. Let's move it now onto the right hand side to simplify this equation a little bit. So equation number 1 at the end of the day becomes and this is equation number 3. And equation number 3 is precisely the model of the system. It is an ordinary differential equation. You see here we have x double dot. It is in fact of the second order. It is not written in a state space representation. So if you want to pass that to a software, you need to first write it down in its state space representation. We're not going to do that yet. And we have therefore completed step 1, which is to model the system dynamics. Okay, so we derived the differential equation that describes the system dynamics, where recall here that x is the position of the ball on the inclined plane. We have derived a model that describes the horizontal position of the dynamical system. All the rest are f, which is an input. This is an input. M and g and phi are constants. K1 and L and K2 again are constants. So we have here a differential equation that involves the state of the system, which is, we'll figure it out in a while, the output of the system, which is x, and the input, which is the force F. Now about the state, to figure out the state, we need to write that in a state space representation. I'm quite sure you can tell me that off the top of your heads, but if not, let's observe that we have x double dot. You know the trick. Whenever you see x double dot, introduce two new variables, x1 and x2. x1 is always x, x2 is x1 dot. It is x1 dot, therefore it is x dot. If you differentiate that second equation, you have x2 dot is x1 double dot, or what is the same, x double dot. Now take equation number 3. I'm writing it down now in its state space representation. Let's copy everything from above. So you see x becomes x1, x becomes x1, x double dot becomes x2 dot. Let's get rid of 3 over 2m. So let's multiply everything by 2 over 3m. And what is that equal to? I will write it on the left hand side. This is x2 dot. Overall, we have an equation for x1 dot is x2, and another equation for x2 dot. x2 dot is equal to that lengthy right hand side. Let's write them one next to each other just to enjoy the result. So this pair of equations is the state space representation of the system. And we can tell very easily now that the state is x1 and x2. Why is that the state? Because you see x1 has a derivative here, x2 has a derivative. And if you want to write it in a little more compact form, you would have to define the system state, which is x1, x2 as a vector, and then what is the derivative of the state. So that right hand side, which I just copied from above, and what you see here actually is nothing but a function. Let's call it f. So the right hand side is nothing but a function f, which depends on what? It depends on x1 and x2. So again, let me highlight that. It depends on x1, it depends on x1, it depends on x2, and it also depends on f. So it's the same to say that this is a function of x and f. And very, very, very compactly, x dot is a function of x itself and the input signal f. So once again, this is the state space representation of the system. And we are almost here, we have almost determined the equilibrium points of the system. So let's take now the state space representation and let's say what is an equilibrium point. An equilibrium point is a pair of the state and the input. So a pair xe, fe, x equilibrium, f equilibrium is an equilibrium point of the system if and only if f at that point is equal to 0. Okay, so let's go back and see what is that function f. This is the function f. It is the right hand side of the state space representation. This whole thing, the right hand side. So you know what we'll do? We'll copy that. We'll copy the right hand side. Let me just copy it for you. Okay, we will evaluate it at the equilibrium point. So wherever you see states or inputs, put the superscript EQ, which stands for equilibrium. Double check whether you have missed anything. No, that's everything. And set them equal to 0. And you don't have to do anything more. So that's it. We have now characterized the equilibrium points of the system. So under what conditions is a pair x equilibrium, f equilibrium? What is the same? x1 equilibrium, x2 equilibrium, f equilibrium. Under what conditions is that an equilibrium point? Well, under these conditions. It is a set of equations. Do you need to solve them? It depends on the application. But here we're not interested in solving them, so that's the answer. We have characterized the equilibriums, and that is everything. What does it mean to be at equilibrium? It means that the input f is equal to that equilibrium value, and x1, which is x, is at that equilibrium position forever. It means that you apply a constant force and the position remains constant at the same time. And if you look closely, x2 equilibrium, recall that x2 is the derivative of x1, so x2 is the linear velocity, is equal to 0. That makes absolutely perfect sense. You shouldn't be moving when you're at rest. At rest, we're not moving, and x2 is the velocity, so that's one thing. Second, if you want to keep your object at, let's say, that position, a certain x1 equilibrium, you can come here and you can very easily solve f equilibrium, which will be, of course, a function of x1 equilibrium. So if you want to keep it here, there is a certain force that you need to be applying. If you want to keep it here, there is a different force that you need to be applying, and so on and so forth. But we're not interested in doing that here. Instead, we will take the original differential equation and we will observe that it's not such a beautiful equation, and we cannot do much with that because it contains a nonlinearity. Which one is it? It is exactly that. We have a third power over here. Well, there is another little problem, but it's really minor. It shouldn't concern us so much. It is that here we have a constant term. This is a constant. 2/3 times g times sine of phi. But our main concern should be that x1 minus L to the power 3. So let's define a function phi, the nonlinear function. Let's call, no, sorry, we cannot call it phi because this is the angle. Let's define a function, let's call it g of x1, which will be x1 minus L to the power 3. And let's linearize that. The linearization of that function is very easy. You know what we have to do. We have to determine the derivative, which is 3 goes down x1 minus L to the power 2. We have to determine the derivative at x1 equilibrium. We have to determine the value of g at x1 equilibrium. And that's it. We can now use Taylor's approximation theorem on g at x1 equilibrium. So let's do that. So this is Taylor's approximation theorem. We should rather write here for x1 close to x1 EQ. Now let's see what is g at x1 EQ. This is this thing. Now before we move on, all these quantities, this one and this one and this one, are constant. This quantity over here is a constant. The derivative is 3 times x1 EQ minus L squared, which is again a constant, times x1 minus x1 EQ. And if you're very observant, which I think you are, you will observe that this is exactly a deviation variable that we call x1 bar. If you're very observant, you will notice that immediately. So now let's go back to the original system, which is, let's copy it from here. It is x2 dot. Let's write just underneath the other equation we obtained previously for the equilibrium point. Let's write it just underneath, nothing more. We just want to have all equations collected in one place, not to have everything, all over the map, just to know where exactly we need to focus. Now draw a line here, take a subtraction, subtract the two equations by part, f minus f equilibrium, and again, if you're very observant, you will observe that this is again a deviation variable. It is the one we call f bar. These constants will be eliminated. Now this is x1 minus x1 EQ, and the L's are also eliminated. We have x1 bar over here as well. And look what we have here. Here is where we need to be slightly more observant. We have a quantity that showed up just before. And up here we have that g of x1 is approximately equal to g of x1 at equilibrium, and so on and so forth. So if what is g of x1 from before, by definition, is x1 minus L to the power 3. x1 minus L to the power 3, x1 equilibrium minus L to the power 3. Aren't these two the same as these two? This is not something that is happening only in these exercises. This is happening always. So if you move that onto the left-hand side, you have, let me write it down to be absolutely clear, x1 minus L to the power 3 minus x1 equilibrium minus L to the power 3. And once again, this is the orange box. So this is that, exactly the same thing, which is equal to this part on the right hand side. So let's write it down again, but this time we will start to get rid of f minus f equilibrium, and we will just write f bar. Group together these x1 bars. And this is exactly the system linearization. There is only one tiny detail, but we know that whenever we have a variable with a derivative, we can always wedge inside here a bar. So x2 dot is the same exact thing as x2 bar dot. Sorry, I have a mistake here. 2k1, k1 should go here, k1, 2 over 3m is the only common factor, k1 is here, and k2 is over here. So this is the system linearization, and I will write it again on the next page, but we are done with the linearization. It is a bit difficult now to have to carry around all these lengthy terms. So let's call this just A, and let's call the other thing, this whole thing, which is a constant, let's call it just B, where A and B are just some positive constants. And we have this equation about x2 bar dot. What about x1 bar dot? What about that? We need apparently an equation for x1 bar dot, but we have that x1 dot is x2, and we have that 0 is x2 equilibrium. Once again, subtract by parts, and you have x1 dot is x2 minus x2 equilibrium. x1 dot is x2 bar. Put a bar here, you can do that always, and that is your second equation. Combine these two, and all we have to do now is write them one below the other, and they are so simple that they can fit in this small box. And we have completed the modeling part, the determination of equilibrium points, and the linearization. Now the determination of a transfer function is absolutely trivial. What is a transfer function? It is this thing. We have a certain input, f, as a deviation variable, and we have a certain output, which is x or x1. X and x1 are the same thing, but uppercase and in the S domain, which is again a deviation variable. We can write either x bar or x1 bar. We will treat these equivalently. And what is this function g of s we have here? In other words, find output over input. So take these equations and apply the Laplace transform. Apply the Laplace transform on x1 bar dot. It will be s times x1 bar. These are all uppercase. So the dots become s's. So simple. You see a dot, you put an s, and that's it. That's everything. Now we have x1, we have x2, however. We need to get rid of x2. We need somehow to get rid of these variables. That's very easy. Just plug x2 from the first equation into the second one, and we have, and see what happens here. We have x1 on the left hand side, x1 on the right hand side. And what do we need to find? We need to find x bar over f bar, or x1. We said x and x1 is the same thing. x1 bar over f bar. So what is that? We need a new page. And we have determined the transfer function of the system. Here is the transfer function. Now simulations. What can we do with the transfer function? We can kick the system. So we can determine what happens when the force that is applied to the system, F bar of t, is a Dirac pulse. We can push it. So we can see what happens when the force F bar of t is equal, let's say, to 1. And we can even shake it. So we can see what happens when F bar of t is sine of omega t. Now if you want to be a little more general, you can say here I want to push it with some force of magnitude a, and you can say here I can shake it with a force of amplitude a. All these for t, non-negative. The kick is trivial. First of all, these have certain names. We shouldn't really call them kick, push, and shake. These are just the impulse response of the system, the step response, and the frequency response. So let's start with the impulse response. What happens when you kick the system? If this is what happens in the time domain, this is what happens in the s domain. What is the Laplace transform of delta? It is equal to 1. Therefore, what is the output of the system? x1 bar of s. It is the transfer function times the input. But the input is equal to 1, so it is just the transfer function, g of s. And if you want to turn it back into the time domain, what is x1 of t? x1 bar of t, don't forget the bar. This is the inverse Laplace transform of g, which is that. This looks like the inverse Laplace transform of sine of omega t for some omega, but we have to be really careful here. This is the inverse Laplace transform. S squared, we need a square here. So put a square root and the square, and here is your square. Take a for a moment outside and put 1. Now what is the inverse Laplace transform? The inverse Laplace transform of what exactly is a sine? We should have here in the denominator the same as in the numerator. So we should have square root of b. Okay, not a problem. Put a square root of b there, put a square root of b here. And now we have a over square root of b, and this is clear what it is. You can check the Laplace transform tables. This is nothing but sine of square root of b times t, defined for non-positive times t. So if you kick the system, this is what happens. Let's write it down clearly. x1 bar of t. Now if you don't want x1 bar, but you want x1 without the bar, recall that x1, this thing is equal to x1 minus x1 equilibrium. And if you very much like, you can move that onto the right hand side, solve for x1, the actual variable, the actual displacement, not the equilibrium variable. And this is the result. This is what happens when you kick the system. This is the impulse response of the system. So simulations here, we've done 1 out of 3. We have kicked the system. Now let's push it. But these things now are just applications of the inverse Laplace transform. So you will see when we push the system, it is nothing more complicated. Again, we have, this is the transfer function of the system. when we push it, we want to see what happens when the force in the time domain is equal to 1. Of course, always we're talking about deviation variables, f bar, not f. This implies that in the s domain we have 1 over s, which means that x1 bar, the output, is the transfer function g of s times the input f bar of s. And this is what we have. And if you want x1 bar in the time domain, you must take the inverse Laplace transform of x1 bar in the s domain. But if you need to find that particular inverse Laplace transform, you need to look at the denominator, and you must observe that the poles we have here are 0 if s is equal to 0, and plus minus square root of b times j, which means that the partial fractions expansion of that will be, if you want to write a over s squared plus b times s, then the partial fractions expansion will have this general form: a1 over s plus and it's not difficult to find from here. I will leave this to you to confirm as an exercise that a1 is a over b, a2 is minus a over b, and a3 is equal to 0. So what is the partial fractions expansion? Given that, you know, you have to formulate and solve a linear system and so on. So what is that? And this is the partial fractions expansion. So take now the inverse Laplace transform of this thing. Let's do it term by term. What is the inverse Laplace transform of that? It is just a over b. And what is the inverse Laplace transform of the second term? That is quite easy now. It's easier than what we did before. Minus a over b, I see here. Why don't we move it outside? So you see what we have. This is the inverse. This will give a cosine. This will just give a cosine with a square root of t apparently here. Let's write the whole thing together. So the time domain function x1 bar, which is the inverse Laplace transform of x1 bar of s, is given by this first term, which we said is equal to a over b, the inverse Laplace transform, and the second one is minus a over b times cosine of square root of b times t, a over b here. And you can take a over b outside if you would like to simplify that. And this is what happens when you push the system. Let's take care of the shake. What happens when we shake the system? Now, usually, I will avoid doing that because usually when you shake a system, the response is more difficult to determine. You can tell why, because if you shake a system, then the input, the deviation variable, of course, of the input in the time domain is a sine of omega times t for some omega. Omega is a real number. It can be negative, but it doesn't make much sense to be 0 because then the whole signal is 0. All right. What is then the S domain of that? What is the Laplace transform of that? It is omega over S squared plus omega squared. Let me write down once again the transfer function. It is A over S squared plus B, which means that the output of the system is the product of these two. It is. Now this is not tremendously difficult to figure out. You have to be a little careful because if you're very, very observant, you will realize here that there is a possibility, it is possible that these two things are equal to one another. And if they are equal, if omega squared is exactly equal to b, we have a double pair of imaginary poles, and we have to treat this separately as a separate case. But to take the inverse Laplace transform here, of course, requires that you go through the standard procedure, which is that you determine a partial fractions expansion, and then you take the inverse Laplace transform of that, being, I'm saying it again, being very careful. We will have something like that. We will have s squared plus, this will be equal to b, s squared plus b once again, so s squared plus b squared. And this is now, it will be a double pair of imaginary poles. But nevertheless, if you like, you can try that as an exercise. Usually we try to avoid taking inverse Laplace transforms on such complicated functions. Instead, there is a beautiful theory that can give us an approximation of x1 bar of t, can give us an approximation for large times t. We will study that in an upcoming video lecture. Until next time, goodbye. But first of all, let me give you a very, very short summary. So what we did today is that we started from the physical system. We sketched all forces. We drew all forces on paper. We started with a more natural, more physical way of thinking, physical in the sense of physics. Then we wrote down the equations that come from Newton's laws of motion. We wrote the system in a state space representation, so that was the intermediate step here from modeling to equilibrium points. We had to write it in a state space representation. We determined the equilibrium points. We linearized the system dynamics. We took this linearized dynamics and we determined the transfer function by applying the Laplace transform. So to go from the linearization to the transfer function, we used the Laplace transform. And then we solved we simulated the system starting from zero initial conditions using the inverse Laplace transform. Starting from zero initial conditions goes without saying, of course. We mentioned that when dealing with transfer functions, because it is always a tacit assumption when you derive a transfer function and you have first of all defined deviation variables, it goes without saying that we assume there that we have zero initial conditions. So this is everything. This is an exercise that covers all the material so far, and it also covers most of the material of this module. So until next time,